let's talk about fundamental groups. So let's first prove that the set of homotopy classes form a group, which we will call the fundamental group. So we're following Hatcher's book. It's a proposition. X is topological space, x 0 point of it, then pi1 x with this point x naught is a group with respect to the operation defined to be the equivalence class of F multiplication with equivalent class of G defined to be equivalence class of F G. This is called product of paths or composition, or maybe more informally called concatenation, which means that so F1 equals J of 0, then you could connect these two paths. So let's give some notations before we, or say recall the notations before we give the proof of this proposition. So firstly, so a path is a continuous function from closed interval 0, 1 to topological space X, and we call it a loop if it further satisfies endpoint coincides. So in our case, when we say this base point is x naught, that means all those path F or J appearing, which means between the between the brackets there are loop with base point x0, which means f0, f1 equals x naught. And then to define what is the class of homotopy or homotopy classes, we have to first define what is a homotopy between paths. So a homotopy of paths in topological space X is a family of continuous maps. So we index this family by t. T is real number between 0 and 1. So this is really a family of continuous functions, and it actually tells you how to transfer or from the first pass, let's call it, which when t evaluate 0 and just f0, so this is f0, and ends at f1. It actually tells you how to change smoothly from your first pass to the second pass, from f0 to f1. And the way is it changes smoothly by a family in the following sense. So f0 itself is a pass, which means this is, if we put this unknown as s, so this is again, this is a pass, so it is a continuous fam from 0, 1 to x, so s takes values between 0, 1. Similarly, this is again a pass from closed interval to x, and they have the same endpoints. This is requiring that f0 of 0 equals f1 of 0 equals, let's say, x naught, and on the right hand side this means f0 of 1 equals f1 of 1, let's denote by x1. And the way we describe this is continuous changing is by introducing infinitely many continuous functions, which means infinitely many passes between these two, by introducing what is this ft of s. So this t is, as we said, parameterize this family. T changes from 0 to 1, but each fixed value of t, this is again a path with an unknown s. And so actually this condition, we could, instead of saying this, just say all the ft has its endpoint x naught and x1. And the way we say this is continuous changing is by requiring that this function of two variables so I is again the closed interval from 0 to 1. Let's say f as t, we define to be f t s is continuous. That's how we say this family of path is changing from or connecting this f0 and f1 is homotopy, which means that if two paths f and g, they are homotopy, this is saying that start with your f. Firstly, they have to have the same endpoints. Secondly, you could find a continuous family, let's say ft of s, such that firstly have the same endpoints, secondly f0s equals f and f1s equals g. Okay. And then one can show that this is the equivalence relation, that, and then we define the equivalence class with representativity of f denoted by f bracket, call it the homotopy class of f. Okay, so let's start the proof. Firstly, let's again quickly kind of recall that this concordination as a path is defined to be we can change the speed. So if first use the continuous function f to starting at f0 and as f1, and then g0 equals f1, and then you continuous with g. The way to connect these two is by this little trick. So I define f2s, so s starts at 0, and then So here again, S have to start at 0 and at 1. When start at 0 and at 1/2, F go through 0, 1. So we just change the speed of F. This is continuous, and then F F1, which is when S equals 1/2, equals J0, which is again when S equals 1/2, and they coincide. This is F0, F1, but also equals J0, and then we end at G1. Of course, it should be something continuous. And secondly, let's check that this is well defined. So what we do is that, just notate that if you have some F0 and F1, they are in the same homotopy class, and then you have some G0 and G1, they are in the same homotopy class, and then the concatenation F0 G0 equals, or say homotopy equivalent to F1 G1, then it is well defined to write the homotopy class of F concatenation with G, which means changing a representative in the homotopy class of F, and G doesn't change this homotopy class of F concatenation with G. Okay, so the way we do it is, by definition, there exists some continuous maps F T of S. And here it has some G T of S. So just notice that then the concatenation of, for any fixed T, Ft concatenation with Jt form a new continuous family which connecting F0 concatenation G0 with F1 concatenation with G1. So in more detail, this is saying that our F1s equals, so this is not very yes, let's do it. So F0s equals our F0s. So this is a very simplified notation. Okay, F1 of S is our F1 of S. That's why we call it Ft of S. It's really very simplified notation to which means when we introduce this Ft of S, this notation is telling you that it is a connecting family of continuous paths from F0 to F1. Okay, so the way we define this is, so what we mean is that this is a continuous map from I product I to X again, which maps S and T to Ft of S concatenation with Gt of S. I don't know if it's a good notation to write this. Usually we just simply denote it Ft and G concatenated with Gt. This is what we mean. And which mean that, so this F 0, sorry, Fs0 is F0s concatenation with J0s, which is here. Fs1 is F1s concatenation with G1 of S, which is here. And this is continuous map based on the fact that ft and jt give you the family of continuous maps. This is a continuous family. Roughly speaking, is called that the requirement that big F with respect to st is continuous is geometrically just saying that this connecting family of continuous path is also curves, they are really changing smoothly. And if this part is changing smoothly and you're connecting with the second part changing smoothly family, of course this connecting this is again a changing smoothly family. That's very roughly speaking what's happening. Then we first define what is called reparametrization and show that it preserves homotopy class. So firstly, a reparametrization of a path f. So again, continuous map from I to x is a composition f with some continuous map from I to I. So which means that we again define a new path, firstly applying this continuous phi, still map from I to I, and then we apply our previous f from I to x. So let's show that this again give you the same homotopy class, which means the homotopy with the previous one, and so the reparametrization doesn't change homotopy class. So the reason is that you just have to construct a continuous function defined I product I to x. Right? So we define this to be just f composed with phi t of s, where let me first define what is phi t of s. Phi t of s is defined to be just a 1 minus t phi t plus t of s. It's just a linear combination of phi and identity, right? And so this is obviously a continuous map with respect to s and t, and so this is just f composed with 1 minus t phi s plus t of s. So let's first just check when our t takes 0. So this is just f composed phi of s. Or when t takes 1, this is just f composed s, which is just f itself. So this gives you a continuous connecting family of paths. Then we want to check the associativity law. Check there exists identity element, identity homotopy class with respect to the product of homotopy or the multiplication we defined at the beginning of the statement, and then finally check every homotopy class has an inverse. Okay, so let's start with the associativity law. So given path is f, g, and h, such that it could make a legal concatenation, which means the right endpoint of f is the left endpoint of g, and similarly right endpoint of g is the left endpoint of h, and then concatenation of both f concatenation with g and then with h, and or you first do g concatenation with h and then f concatenation with this path. Both are defined, and what we have to do is we have to check that their homotopy class are the same. They represent the same homotopy class. And then just by definition of this concatenation, we could write it down explicitly. So when you first do concatenation f with g, then with h, then h takes half time, and concatenation of f with g takes first half of time. And so each part f and g takes a quarter of time, and you just make this. So by definition, this is just smoothly changing, this is just linearly changing, and make sure that s goes from left point to right point, f start from f0 and at f1, and then g0 and at g1, and then h0, h1. Similarly, we have second path, which f takes half time and g concatenation with h takes other half time. And then we want to show that they represent the same homotopy class. The way to do that is to realize that by what we have introduced as reparametrization, this two path is, let's say more precisely, we could reparametrize the first f concatenate with g and then with h to become this f concatenate with g concatenate with h. The way to do that is we changing the speed. We use this phi there to change the speed of value of f with respect to variable of s, right? So we, for example, if you take the first part is, let's call it phi f, the part you compose with f. If you just take it to be 1 over 2s, then you're changing the speed. When s goes from 0 to 1 over 2, this phi f of s slow down the changing of s. So when s goes from 0 to 1 over 2, this phi of s goes from 0 to 1 over 4, right? And then this f evaluate on those gives you again f0 to f1, and the composition of f is phi of f in the form f of 2s. So basically you are changing from this path to this path. You're just changing the speed of f. F it still goes from f0 to f1, but with respect to the changing of s, the value of f is changing more. It's changing more slowly. And with doing this, you rely this tool to just reparametrization. Actually, even without this precise description here, you can still say that this is just reparametrization, so they must be homotopy equivalent. And then let's say that you could have identity homotopy class. So in general, let's say if you have a path f from I to x, let's say without assuming that it is a loop, then you could still say that this f concatenate with gamma f1. Let's call this gamma f1 the constant path, which with this base point f1, which means that when time goes from 0 to 1, this path doesn't change at all. It is always on that point f1. And then you check this concatenation of f with gamma f1 is, by definition of concatenation, the first half of time f goes from f0 to f1. In the second half of time, it doesn't change at all. It's constant. And so again, because this is a reparametrization, for similar reason, by result, this will be again homotopy equivalent. So they represent the same homotopy class. Similarly, you could say that it has a kind of a left identity, which is first take constant of the first half of time at f0, and then in the second half of time f goes from f0 to f1. This is homotopy too. f goes from f0 to f1. And so when we're talking about loop, so gamma f0 and gamma f1 actually it's the same homotopic class, and this gives you both left and right identity. This would be the nerd element of this group. Okay, so finally let's check that any homotopic class in this set has an inverse homotopic class. And so still, let's say first say in general, if you have a path f goes from f0 to f1, then I could define what is called the inverse path of it, denoted by f bar of s, just defined to be, instead of fs we write f1 minus s. So we see that when s goes from 0, the time goes from 0 to 1, it goes from reversing the direction from f1 to f0. And so its composition is a path which forms a loop, right? Because it comes from x0 and go back to x0. Actually, we want to show that even in the general case, even you're not started with loop, you just started with the path. We want to show that f concatenated with its inverse is homotopy equivalent to this constant loop gamma x0. The way we do that, you have to construct a smoothly changing family connecting this f concatenated with this f bar and this gamma x0. So the way is we are going to like restricting how far it could reach coming back, right? The way we do that is firstly we define this ft as to be f1 minus t times s. So when you see that when s goes from 0 to 1, this the value of fts is does not really reach from f0 to f1. Instead it only reaches, so this is f0 f1. So when you look at this, when s goes from 0 to 1, it stops halfway, and this is f1 minus t. As you can see that if I keep shrinking t, if I keep increasing t, and this length will be keep shrinking. And let's define this HGS to be ft concatenated with ft bar. So this is really starting is this one, and then when you increase t, this will become stopped at halfway and then coming back. And if you keep increasing t, this will finally stop at this point. So this would be our h0. This is our h1. And so this tells you that this must be homotopy equivalent, as we have constructed what is this connecting family of passes. And similarly, just by interchanging f bar and f, still you could show this is the case. And this corresponds to the same homotopy class. And so you constructed inverse for any loop in this homotopy class. And so we have finished the proof of this formal group.